Our next topic is stable nuclei. In this topic, we will study about the stable configuration of stable configuration of nucleus, or we can say that why some combinations of neutrons and protons are more stable than other combination. So in this topic, we will see uh, the the configuration of the nucleus for different numbers of neutrons and protons. So to start this topic, we just start from this graph. So in this graph, you can see that the graph is plotted between the proton number Z and the neutron number N, shown in figure 1. So this graph shows two different lines. One is a straight line and some other line is a little bit uh, in the shape of curve. So the line which shows straight, so this is a straight line. What this line shows that n equal to z. This line shows that n equal to z. So n equal to z means this is a stable nuclei configuration, while the other curve, which is a little bit deviated from the original path, this is practical line, or we can say that this is the line that we have drawn by the experimental data. So the original configuration of the nucleus is followed by this second line. Which line? This line. So what this line shows, the straight line shows that the number of neutrons and the number of protons are equal. If the number of neutrons and the protons are equal, then the nucleus gains its stable configuration, and if it is not equal in number, that means if n not equal to z, then the curve deviates from its paths. Practically it is deviates, and it shows that the region of light nuclei, so this is the light nuclei region which is more stable, and this is the region of less stable nuclei, because in this case the number of neutrons is greater than number of protons. This region is more stable because this region shows the number of neutrons and number of protons uh, somewhat equal. So the tendency of deviation shows that as we move from lighter nuclei to the heavier nuclei, the nucleus becomes less stable, and this less stability of nucleus is due to the unpaired neutrons and protons. Unpaired neutrons and protons, it is somewhat like atomic structure in which electrons forms opposite pair, which follows the Pauli's exclusion principle. Some same law, Pauli's exclusion principle, obeyed by these neutrons and protons. Why? Because neutrons and protons are also spin half particle, and so they forms pair when they both spins are opposite in the direction. So they forms pair and they becomes stable. So the nuclei, so the nucleus in which nucleons are unpaired are less stable, and these less stable this less stable nucleus shows alpha and beta decay. So, by means of alpha decay, a nucleus decays two proton. A nucleus emit two proton and two neutron. So, after emitting two proton and two neutron, the nucleus slightly deviate backward as shown in figure 1. So, as number of neutrons and protons reduces, the nucleus shifted backward, and or we can say the difference between the original the difference between the original and the stable configuration line reduces, and in this way it gains stability. So the process of alpha decay and the process of beta decay, they are happens because in this process the nucleus gains its stability. So more the number of neutrons and the protons, they are sorry the more the number of unpaired neutrons and protons, they are less stable, and they shows the alpha and beta decay. So you already know about alpha decay, in which two proton and two neutrons are emitted, and in case of beta minus decay, one neutron gets converted into proton and emitted one electron, and in case of beta plus decay, one proton gets into converted into neutron and emitted one positron. There is one more probability of reaction. In this is known as electron capture, in which the innermost orbit of atomic orbit, uh, for suppose the first orbit, in which electrons are overlapping on the nucleus. So the proton of the nucleus absorb these overlapping electrons and get converted into neutrons. So this equation is known as electron capture. Okay, so by this method, the neutron, which is less stable, converted into more stable configuration. Okay, so this is the case, and so one question comes in mind: why this? Why the different nucleus shows that number of neutrons greater than number of protons? So the answer is uh, because the number of protons, if number of proton is greater, then they shows repulsive forces between, because the two protons repel one another due to the repulsive forces, Coulomb repulsive forces. Also they shows nuclear forces, which is always attractive in nature. So short range nuclear forces are always applicable on the nearby nucleons, while the repulsive forces between protons always appear there for a little bit more distance. So the repulsive forces between the protons uh, appear throughout the nucleus, and to overcome this repulsive forces, there are some number of neutrons, because the neutrons always shows attractive forces, because they don't have any positive or negative charge. So only the attractive forces are there. So protons are positively charged and repel one another electrically, and so that an excess of neutrons which produce only attractive forces is required for stability. Hence, in figure 1, departure of curve increases from n equal to z line as z increases. So 60% of the stable nucleides have both even z and even n. These are called even nucleides. Nearly all the others have either even z and odd n, or odd z and even z, with the numbers of both kinds of being about equal. Okay,